Good morning, it's the physics video lecture once again. Psci 168, video lecture 37. And we're going to continue discussing the laws of electricity and magnetism. And today I will show you one more important law referred to as Faraday's law, and then a very basic electric motor with which we can also understand electric generators. At which point we really have everything together to understand energy as we've undertaken over the course of this semester. So good, let's look at the laws of electricity and magnetism. And the way we had it so far is we just talked about electricity, electric charge, forces and fields, and I'll say electric fields, and then also currents, power formula, right, voltage, etc. So that was our study of electricity, electric fields, voltage, which is referred to as potential, etc. Okay, so we've studied electricity. Then we did a brief study of magnetism. And we remember, so I'm going to write magnetism and the magnetic field, which we call the B field. Right, electricity has an E field and magnetism has the B field. And some properties, of course, very interesting properties having to do with magnets. Fine. At that point, they're separate. They don't have anything to do with each other. Now, the next law that we found, I forget what order I did it in actually, but we have electric currents. I may have written it in the other order last time, I'm not sure. Electric currents produce magnetic fields. And I demonstrated that with a pretty rudimentary demonstration, but I had some coils of wire, I sprinkled some iron filings there, I'd let current go through it, and the iron filings line up as though there were a magnetic field there, which in fact there is. So electric currents produce magnetic fields. Then we had magnetic fields act on electric currents. So magnetic fields act on electric currents, and that is a force. Okay, the force, exclamation point, and that's going to give us motors. And in fact, I'm going to show you a very basic motor that makes that all clear. Now the next law, I'm going to first do a demonstration for you. First, we're going to define what's called a magnetic flux. Now, we already know that the magnetic field is a vector field, and so we can imagine a magnetic field in this direction, for example, between the poles of our strong magnet, and then we're going to imagine that magnetic field going through a loop. Okay, doesn't have to be a loop of wire here, but we have different kind of wire coils. At this stage of the game, you can just imagine there's a window of a certain area, and we have a magnetic field going through that window. That's what we call the magnetic flux. I'm going to define it, Greek letter phi sub b it's just equal to B times A, where A is the area. Okay, B we already know, A is just an area, and it has to be going through. So for example, the B field is coming at me, it's B times the area of this tray. If I turn it sideways, then the B field is not going through it. So we also have to have perpendicularity in the B field in the area that it's going through. Same thing with this loop of wire, coil of wire here. So B times area here, if that's fine. If I turn it to the side, there's zero flux. Okay. And so flux is another word for flow. So right here, where B is perpendicular to the area. Okay, that makes sense. So that's the magnetic flux. Now we can imagine a magnetic flux. I just grab a bar magnet. So we're familiar with these. We had these bar magnets here the other day. They like to grab each other. Good. So we have say we have a bar magnet like this, and we know there's B field coming out the end of the bar magnet. That we can say there's a flux. Okay, there's a flux through this surface here, bounded by the green curve. So I'll even sketch that. Example. So let's see, can we have some perspective here? So we've got a loop, area A, and we have a magnet, north pole and south pole, and I'll even draw some field lines, leaving the magnet the way we saw they do. So we would say, yeah, there's a flux of magnetic field through that loop, which is in profile right here. And if I were to move the loop away, the flux would get weaker. If I were to twist the loop, the flux would vanish. There would be zero flux. So full flux, zero flux. You can imagine, a breeze or something, some flow of air or water flowing through this surface area. Okay, so now for the demonstration, and we're not even using some commercially prepared loop. We had one of our people here just wrap a lot of wires into a loop here. So there's a donut-shaped coil with many turns, and we're gonna send some magnetic flux right through this thing. By approaching it, I can twist it, I can do all those things I was talking about. I can send this magnet closer or farther away. Okay, so what we're going to do is hook this up to a galvanometer, and that means I have to bring this into view. So let's go down here. Good, here are our demo objects. So this device here, big old-fashioned galvanometer, it measures current flowing, okay? And that needle will go back and forth. I'll kind of release the safety on the needle here. So there's no current flowing through here. This is not a battery, this is just a lot of insulated wire, insulated copper wire. But what I'm doing is making a complete loop, okay, complete loop. The great number of turns means we're gonna measure a lot of flux, because for every turn of green wire, we're getting the same amount of flux. Okay, so there's maybe 100 turns. Okay, so here we go. I'm just gonna lay that there. You saw the needle move. Okay, we didn't touch this with any kind of battery, and yet the needle's not moving now. Okay. Now if I retract this, notice that the needle moved in the opposite direction. So again, I'm going to bring this in here. Okay, you got to give it some time to dampen out. Okay. And now when I remove the magnet goes in the opposite direction. So there's a law here about what creates an electric current. And in fact, what creates an electric current is an electric voltage. And what creates the voltage is the change in flux, okay? So it's not the flux itself, but it's the change in flux. I'm gonna write this down as our fifth law. And this is so famous, Faraday's law. And then I'll demonstrate it a little bit more. A changing magnetic flux produces a changing voltage. Magnetic flux. So we always use the letter B. That's nice. That's the thing right up there. So that is the phi sub B actually. So I have the definition right up here. I'll say a changing magnetic flux produces a changing voltage. And from that, we get a current. From that alternating voltage, we get an alternating current. Well, let's not get ahead of the game. Okay. So current, comma, if there's a circuit loop. Okay, so let's look at this again, because this is the most basic thing. You just have wire. There's nothing going on here. Let's see. I'll put the magnet here. Okay, and this time I'm going to change the flux by twisting it. Okay, if I give it a twist, you see the needle go. I'm going to reverse the direction of the magnet, and I do the twist. Okay, so here I'm just changing the flux. Those are pretty slight. Okay, let's get a more dramatic one. There we go. So there are different ways to change the flux. Now I don't know if we have a strong enough magnet here. In principle, I could spin the magnet inside of the, yeah, that does something. Any way at all. That's the content of Faraday's law. Any way you change the flux whatsoever, you're going to generate that voltage. So any type of twisting and turning I do here, turning it's actually good because then I'm changing north to south pole rapidly. So let's try that. Let's turn this here. All right, so you can imagine spinning this magnet. Okay, so or we can drop this magnet on top and lift it off. We can change the orientation by giving it a half twist, and it'll go the opposite directions. Okay, and on and on. So that is referred to as Faraday's law, and it's absolutely key in the generation of power, because now I have to move up to a kind of an industrial application. Let's bring this a little closer here. An industrial application would be some giant magnets, some giant coils of wire, and a river spinning these turbines, okay? And that would be how power is generated. With this application, you can't feel it, see it, and you can't even feel it, how much power can be involved, okay? But if you have a fixed magnet and an actual load, then you're actually going to feel resistance as you turn this, because this needle represents a motor that's doing work. Then as we do work here, getting some motion there? Yes, we are. As we do work here, we're doing work, transmitted through these wires. Okay, let's see. We have Faraday's law. That's pretty good. Let's send this up here. Here I'm going to put this all up. For the moment. So yeah, our laws of electricity and magnetism are in some sense complete, right? Everything having to do with the electricity and its field, everything having to do with magnetism and its field, and then the combination where the electric current produces a B field. The B field acts on the electric current, I demonstrated those, and then the magnetic flux, the changing flux. This is the law here. The changing flux produces the changing voltage. And if you spin, say, a coil in a fixed magnetic field, you're going to get the alternating voltage and the alternating current. That's actually how it's done. You spin something. You either spin the coil or you spin the magnet. You turn a crank. So what I want to do next is show you a very simple electric motor, and I will draw that. So that's this topic here. So you've got the electric currents, the B field's acting on electric currents, getting a force. So actually with these laws here, you have the electric motor, and you add Faraday's law, you have the motor and the generator. So I'm just going to write here electric motor. Now the little motor I want to demonstrate, this is the kind of thing we actually have to have in class and pass around and observe and play with. But instead, I'm just going to set it up and demonstrate it and encourage you guys to possibly try to build one. Let's see, I need a little board here for starters. Okay, yeah, we'll leave that up there. So a model electric motor, and this one is very simple, but the simpler the better. You actually have to see and feel everything that's happening. So let's just call this an electric motor. And what it's going to have is a C-cell battery. I'll even draw it. You've got a battery like this. And insulated copper wire. The type I'm using is lacquered, so it's actually copper colored, but it's insulated. Insulated copper wire. And then with that insulated wire, what we do is we wrap it around the battery several times, and we end up with a loop that just fits right around the C-cell there. That's a good way to do it. So we have a loop of wire, and then the third thing we do is we put it on a metal stand, and here's where it gets interesting. But I'm just going to use another color. So this is going to be metal. And here's where we're going to put the C-cell. Okay, so we have a battery here, and then we have magnets. I'll just write North Pole, South Pole. So we have a magnet here with B field pointing up like that. Okay. Or should I do red for the B field? Let's do red. Okay, so these are copper wires. This is the battery. There's a magnet here, so we know we have B field. Okay. And here's my point. When that copper loop Oh, and we have to scrape off the insulation. Scrape off insulation. And we do it in the following way. I'm going to say we've got a side view and the side view, the end view. The end view of the loop, wire loop, is that we're looking at the wire on end, and then of course there's the loop right there. And what we do is we scrape away some of the insulation so it's half. I could do a little perspective on this too. So this is a much thicker wire than it really is, of course. Okay. And then, you know, it goes into all of its loops and comes out this side. Okay. But what we do is we scrape away the insulation so that the bare copper is on the bottom half. Scrape away the insulation. And what now happens here, I'll indicate some little bare copper there as well. What happens, and this is a small picture, but we're going to bring it up closer to the camera in a moment. What happens is, here's this loop with the magnet right under it. There's no flux. When I turn it, there's flux. When I turn it again, there's no flux. On the one hand, if we just look at it in the fixed position though, there's a current going through this entire, let's make this the plus side. So we've got a current here, current going back. We have current going, in this particular instance, clockwise, and the current is acted on by the B field, produces a force and a torque. Okay, I'm going to put this thing together and then show it to you guys. I'll hold it up close to the camera and have a look at what this looks like. Yeah, good luck. Here, let's do this. So where's that little camera I'm talking, not camera, that little motor I'm talking about? I'm gonna bring it up on the tray here. So here's the device. This is a C-cell battery, put that there. These are some 3 magnets, and you know, they're disc magnets, but we talked about the magnet can be flat, and there's the repulsion and the attraction. Okay, so I have 3 of them. And then here's the frame I was talking about. And actually here's the loop. I'm gonna hold this up to the camera. Yeah, let's see if we can do this. Here we go. Okay, now not so good. Okay, not so good. But when I bring the whole machine up, I think we'll get better focus. So anyway, here's this loop. If we're looking at this thing on edge, there is insulation scraped off towards you guys. If I turn it a half turn, the insulation is not scraped off. So if I put it in here, half the time it'll make contact, and I'm gonna put the battery in this end of the frame. And now I have a current, okay? I have a current, but a current's not enough. What's missing? What's missing is the B field. So we'll put a magnet in here, and here we go. The motor turns. Okay, now it's kind of humble maybe, but I'm gonna bring it up to the camera. Ideally, we would all actually have one of these and really carefully play with it, because there's a whole lot going on, and yet it's very simple. But yeah, I'll bring it to the camera and I'll demonstrate a couple of things. Maybe I'll put it on this side of the tray. It's spinning away. Yep. Now we're talking. Okay. So there's the magnet. There's the rotating. Okay. So make sure you realize what our circuit is. The battery, and then the copper wires. And you can get a screenshot of this too. Oh, slowing down. Here we go. Okay. I'm actually going to try to zoom in on this. Let's see here. Wish me luck. That. What a profile. Okay. There we go. Okay, I want to say a few things. It's hard to demonstrate these things in person, but with my picture, I'm going to draw a slightly bigger picture and discuss a couple of the things that are possible with this machine that I'm having trouble doing in real time here. So let's just do a larger version of this. And here are some of the experiments we're able to do. So this is just the bigger version. We've got the battery. Okay. And we've got this here. Just a slightly bigger picture. How about we use another color? So yeah, this thing was rotating if there was a magnet here. So I'll just indicate this with the north and the south. Thing was spinning in the presence of the magnet because of that law that I've erased, in which if there's a current through this thing, then the B field is acting on the current and producing a force, and it produces a torque. So one thing you can do with this little machine is actually carefully hold it with your finger, and you'll feel that little bit of torque in the presence of the battery. Another thing you can do is, and this is really interesting, is suppose I take a magnet above it and do it like this, north on the bottom, south on the top. Then those two vector fields, remember vectors add like arrows, we learned that a long time ago, those two magnetic fields will cancel each other. So if I bring these two magnets up to each other symmetrically, the thing will stop. Okay? It'll stop because the magnetic fields, they're like vectors, they're adding to zero. Right? The up one and the down one are canceling each other. So, okay, that sounds good. What if I arrange them this way, south, north? Then I double the strength of the magnetic field and the thing turns a lot more rapidly. So these are experiments we can do, but you really have to have this thing in front of you. You know, you have to have it. A couple of years ago, we were actually able to make, I had a pretty small class. We made one for everybody, and then, we could experiment around with it. But that's the principle of the electric motor, and everything that follows in electric motors is just is a further development. Okay, but this is it. It's got the torque, it's got the current, and I'm going to use this same model to talk about a generator. So let's go ahead and take this second picture here. And imagine we have a crank with a handle that we can turn and remove the battery. Now we have a generator. In fact, we'll take these. Call this A and this B, and we'll have delta V AB will get a voltage if we just turn the handle. Okay. So right here, we're taking this picture. Maybe you guys should do another one, but I'm going to stick with this one right here. A generator. This is a generator. I'll just generator. So what do we have? Now for the generator, let's make sure we have south, north, and then south, north, so that we really have some good, strong B fields going this way. We turn the handle, then Faraday's law is in place. Turn the handle so we're spinning this wire coil here, and we're getting a voltage right here, and if we can hook this up to a circuit, we'll get a current. Okay. But by turning this is going to be alternating. And this is what you have in your home. You have actually 120 volts alternating voltage that plugs in the wall. And if you want to hook this up to some device of yours, somebody has to be turning the handle. Okay? And that's where we go back to our hydropower, our heat engines, and so forth. So this is how simple it is. This device here without the battery, okay, very miniature version here. If I spin this, I'm actually going to generate alternating voltage in these copper wires, at which point you could run connections to your devices and power them. This is a very, very weak version, okay, but that's the principle. So let's even right here apply work here. And then hook up some device here, and you supply the work turning the handle, and this device functions. So supply work here, and connect device here. So really, the simpler the better. The simpler the better to see the laws of electricity and magnetism at work. Okay, good. We're going to leave it at that. We have a couple more hours, and I'm going to talk about transformers and the grid next time. And then on the last hour, we'll just wrap things up and do a review for the final exam. Okay, good. See you next time.